Hello everyone, here in this video I will explain how particle swarm optimization works and how you can get basic understanding of this MATLAB program, and also how you can optimize your own objective function after getting the basic understanding. Previously, I have made another two videos on the PSO MATLAB code, but I think so this one will be the complete and more advanced than the previous ones. So this MATLAB code is taken from the ERPs, and they have the rights for its license. So here you can see the license terms. This video is basically for the educational purpose and how you can optimize your objective function. So let's start with these lines. Let me first run the program here. Let me run program again. So I just run the program here. So this means that I have to clear this command window section. This is the command window section when I have to put this instruction and hit the return. So I have just clear everything from my command window. And for clear, this is to remove everything from the workspace. So all the variables from the workspace have been gone. And next, the close all instruction will remove all the figures which we have in our figures. So it will remove all the figures. So now we have our main part, which is the problem definition, and in the problem definition part we have our objective function, or you can say the cost function. So here we have the alpha x, which is the function. This will represent the sphere x. So alpha x is representing the function sphere x. So later on you can replace this function with your own objective. So we are directing into this sphere is actually we have a file here, sphere.m, which is a function file. Let me open that. So in sphere.m we have our objective function. So whenever we call a function, just so this is the function sphere. Here you can see that we have function sphere, which is actually the cost function. So let me left click here and let me click on run. So I want to run the program in steps. When I click on step, and here you can see that we have a cost function, and inside that cost function we have sphere. So sphere is actually you can say a variable or another function. So later on let me select this cost function, and here in this bar you can see that we have three green lines. Let me click here at this point. Okay, so here we are calling the cost function, means we are calling the sphere, and in the sphere we have our objective function. So in this case we have this objective function. So in our objective function we have to give the value of x, and it will give us the value of z in form of output. So what I mean is that if this is the objective function and this x is actually input and this z is actually output, so we have to get this input from the PSO file pso.m, and then we have to give this z into back into from sphere dot m to pso dot m. So we have to give this z output from sphere dot m to pso dot m. We are here we are here in the sphere dot m, and then we have to put that z, so that z value will be stored in the particle dot cost file, so in the variable particle dot cost. Okay, and now at this point, this is the number of the decision variables. So if our input is x, so nvar means we are considering the 10 entries or 10 numbers for our x or for our input, and this is the var size, which defines the size of decision variables matrix. In this case, it will be 10 cross 10 size of matrix for our VAR VAR size or decision variable matrix. So minimum and maximum, so lower and upper bounds for each number for the x. So if we our x have 10 numbers, first and the second, third, fourth, fifth, and so on. So for each number we have minimum minus 10 and maximum bound is 10. So similarly for other uh, entities or other numbers for x, we have minimum and our maximum as minus 10 and 10. I will show you that in a while. And the maximum iteration are considering here the 1000. Number of populations considered are 100. So these parameters defines the maximum number of iterations and the population size. So population size, you can say swarm size for the PSO algorithm. And next here we have PSO parameters. So W and WDAMP C1 and C2 are the PSO parameters. They control the behavior of particles in this form during optimization. So W is the inertia weight, and all other details are mentioned. You can choose to use either these parameters or the commented constriction coefficients below, depending on the so this is the commented section. So if you want to consider these functions, you have to just uncomment these, and you have to comment these. So you may utilize based on your own choice or your. And then here we have our velocity limits. So these lines set the velocity limits for particles in this swarm based on the variable bounds. And then next we have our initialization. So here in initialization part, we are initializing the variables in which we have to put our PSO variables data into. So let me click here, left click here, and let me click on continue. So when I click on continue, I am at this point, and this will be switch to this point, and it will execute all the lines instructions between this circle. Let me click on continue. Oh, let me click again, and let me click on continue. Okay, and now I'm at this point, and here you can see in the workspace we don't have the empty particle position or empty particle position. Let me click on step. So here you can see that we have empty particle. So what dot is doing is actually creating another variable inside a variable. So normally just like this one, maximum iteration, we have initialized a variable, and whenever we put a dot next to a variable, we are creating another variable inside a variable. So this is the same. So means this is the variable, and inside this variable we are creating different kind of variables. So let me show you. So this is the input particle. So in the empty particle, we have currently initialized position. Let me click on left, and now we have initialized cost inside the empty particle. Click on left, now velocity, and now inside the best, and inside best we have position and cost. So inside best we have position, and let me click once more step, and it will be cost. So you can also see this symbol before the best, and there is a difference between this and this symbol. So this will represent our basic position of our input, or the number of bounds, the number of variables which we want to represent. So this will represent the number of variables. I mean, there you can see you can say their size, and this will be the cost. For example, we have 10 numbers, and when that 10 numbers will get into this sphere, we will get our z, and that z will be stored into the cost. Okay, and here this is the rep mat, and if you don't know about this thing, just copy that and put here doc, and put that variable. So this is the variable for the MATLAB predefined variable. So this have certain meaning. So this have a certain meaning, means rep mat. So rep mat returns an array containing n copies of a in the row. So what does is actually doing is that we have to create these variables, 100 variables. Okay, so we have to create 100 empty particles. Means what's actually inside the empty particle, we have to create that certain copies, 100 copies, as our npop is 100. So let me click on step. Okay, so now previously particle was not present, and now we have initialized this variable, and inside this variable we have 100 copies of this empty particle. Let me open it. So now as our population is 100, so we have 100 entries. So these will be the basically the inputs, number values of the x. So each position have 10 value of x, and then this will be the output from this sphere, and then this will be the velocity. Okay, and initially we have put our global best dot cost as infinite. Let me click on step. Okay, so basically the particle is that in our PSO main algorithm, or in this start of this algorithm, which is starting from here, we have this data and we have to fill this data. So later on, when this we have filled out all the data, we will make a comparison. And now at this point, let me click on step, and now we are unifriend. You may again let me open the doc, and you may search that unifriend. So you may search more about here, how to, what actually it means and how you can get benefit. So we can utilize this unifriend in a different manners, and here are the examples. So if you want to explore more, you can explore here, or you may read about relevant instructions or relevant MATLAB commands here. So here we have minimum, maximum, and our variable size. So we have 10 variables with each minus 10 and each maximum of 10. So we have to, means we have to create 10 numbers. So here you can see we are directing into the particle. So this will be our instruction, sorry, this is our input, and this is our the instruction, and this will be the output. So let me show you particle position. Right now we have empty nothing, and when I click on step, here you can see that we have filled this. So let me double click here, sorry. maybe this will not work. And let me show you that we have 10 numbers. We have 10 numbers with minimum and maximum bound between minus 10 to 10. So we have 10 numbers. So if we have more number of variables, as per if our objective function is different, we need more numbers. Then uh, here uh, uh, here, if for example if we have 20 Decision variables, here we have 20 numbers. And maybe based on our number of variables, we have different bounds. Maybe we have bound between -2 to +2. So it varies, depends upon the situation. And okay, anyway, so the purpose here is to here are the 10 numbers. Okay, and here we are initializing our velocity factors, which is 0, so it will be 10 velocities. And now at this point we are going into our cost function. So this is the particle I position. So let me show you. You may also check particle I position. I is 1, so we are at first position, particle I position. So you can see this number. Also you can copy the variable from the this script file and put into the command window and hit enter button. And here you can see that we have the same numbers. So these are the same numbers. So we are the 10 numbers. These 10 numbers, okay, these are input to cost function. So what I mean by input means we have to put these numbers into our cost function file. So we now we are putting these 10 numbers, which is actually the input, and we have to put into the cost function. Now cost function is actually sphere.m. So let me left click here, start another debugger. Let me click on step. Now I am inside that. So here at this point you can see we have a different color, and here is green color, which means this one is active right now and it's not active. So here we have particle I position, and now in this file we have x. So different names, but they have the same position. This is on a right side of sphere, and this is the right side on the cost function. So right now the same name is not important, but the position is important. So particle I position is representing the x. So here in x we have exactly same number which I have here. So now we have our 10 numbers, and based on 10 numbers our objective function will calculate it and we will get our z. So let me click on left, and now I have calculated the z. Let me click on z here. So this is the 332. So at this point this is the z, which is 332. Let me click on step. So previously in sphere.m we have z, and right now we have particle I.cost, which is exactly the same, which is actually 332.0316. Let me click on step. Okay, here you can see that we have 332.0316. So we have the same number. So similarly, we have to repeat this loop starting from number of population, and then we have okay, let me do it a little more. And this is the particle I position, and this is the particle I cost. So this is actually the personal best. So this is the personal, so this is actually the personal best, it's not the global best. Global best will be when we have 100 swarms, 100 particles, and each particle have its own position and it have its own cost. or the objective function value. So this will be the p best, and when we will find which one is the best from all the 100, as our population or swarms are hundreds, so that will be the global best, which is next here. And now we have this cost. Let me click on step. Let me remove this because we get understanding about this variable. Click on continue. Okay, and right now we have simulated this for twice. Similarly, let me click on step. So we are putting particle best position, and so particle and then best. So it's the personal best. It is this the numbers values, and it's the cost according to that. And initially we have global best. Okay, and now we have to compare the. Okay, let me select this variable. Okay, so when we first time run this program, we have personal best. Let me show you. Okay, let me run the program again. So let me make sure everything. At this point, we have only so I run this program again, and at this time we have a different cost. So this is possible, and because the particle swarm optimization or other optimization algorithms work on the random selection nature, so it's possible, so no need to worry about that. So definitely we have different numbers this time, and I have run the program another time, and we have different cost based on that, but the final results will be closer when each time you run the program. So now at this point I have the global best, which is infinite, and I am comparing the global best with the personal best. So particle I, let me select this thing. Let me show you. So this is the infinite, and this is the personal best of the first swarm or first particle, so which is the 271, which is definitely is the less one. So now we are putting the personal best in as the global best. First time we will do that, and next time, let me click on. So next time we now our global best is set to 271, and let me show you the personal best of the second particle, so which is actually the not best, which is actually the more sorry, it will be better this time. Let me click on the. So we have to choose that if our global best, if our personal best is less than global best, so we have to consider a better value, means we find better value when we have our personal best which is less than the global best. So this time our personal best is more than the global best. So let me show you global best dot cost. It is the global best and global best dot cost, which is 271. So this statement is not going to converge because we have less global best and personal best is more. Let me click on continue, and let me show you. I can also see that particle best dot cost, particle and best and cost. This time we have 306, and here we have, I think so, 272 or 271. So this will not be replace that. So similarly it works. So let me click here. Let me get out of this loop. Let me click on continue. I'm out. And let me show you how much global best we get right now. So we have 133. Now let me show you that using the, so here are different entries. We have 100 populations, and here you can see some are good numbers, some are worst numbers, but 133 is the best. So inside our global best, we have the cost, and also we have the 10 numbers. So these are the 10 numbers which we are actually defining. So which 10 numbers are the best? So right now these 10 numbers are the best, which give us the minimum cost of 133.0073. So now we are getting back into our PSO main loop. Here is our maximum iteration. When you will move your cursor there, you can see the number and iteration. Let me click on step. And right now we have our velocity parameters, which we have considered previously as 0, and apply velocity limits, mirror effect, and this kind of stuff. So this is the number of iterations. In each iteration, for for one iteration, this loop will complete all the population. Means for first iterations we have to complete all the populations, and for next iteration we have to complete all the populations again. So 141 and 149. So this loop, when we have first iteration, so for first iteration we have to complete all the populations, and at the end of the 100 populations we have to run this line, this line, and then at this point we have to start another iterations, which is actually the next, after the completion of the first iteration, then we have to go for second iteration. So this is the particle I velocity. This line updates the velocity of the current particle, which is actually the particle I. Based on the PSO equation, the velocity update is influenced by three components here. So the first one, which is actually W, which is actually the inertia, and the C1, this factor, this is actually the personal learning, and the C2, this factor is actually the global learning. Here, as I explained previously, W is inertia, C1 is the personal learning coefficient, and C2 is actually the global learning coefficient. And this one, the rand, VR size, generate random numbers creates random numbers based on our the decision variables, which is actually the 10. So if we have 10 decision variables, we have to generate 10 random numbers. So these lines ensures that the particle velocity. Now next, we have apply velocity limits. So these lines basically are ensures that our velocity remains within the predefined velocity limits, which is actually VEL MIN. So when I chose this variable, you can see that we have here we have defined here. So this is the well max. We also have defined this variable previously. Okay, so these lines just make sure that our velocity limits are within the predefined range, and this is to that the our updated velocity updated position is based on our, I mean, this is the updated position or the updated numbers based on the random selection of the particle plus the velocity parameters. And there is a velocity mirror effect. If particle position exceeds the bounds, this line reserves its velocity to the bounce it back into the valid range. So this is known as the velocity mirror effect inside the particle swarm optimization. And next we have apply position limits, and then we, if these conditions checks if the current particle cost is better, then it's again this is another check. And we have to this condition checks if the current particle cost is better cost than its personal best. So here is the evaluation part here again. As we have updated our input or our position, and then we have to put that numbers into our cost function. So let me show you this thing. What does actually it means that previously, for example, if our this is actually our the space we have to work. So for example, our decision variables are three numbers, okay, instead of 10. And let's suppose that after these updates, if our numbers are going there, I means from upward to downward, if we are getting results, then velocity factors and these updates will help us to move our particles position. So these lines help us to move our particles positions toward the downward. So that's how the numbers and the position is same. So number is actually represent the position of each particle within this workspace. So later on we have our personal best. So right now this is the cost, and we are comparing this thing with the personal best, and later on we have to compare this thing with the global best. So let me click here and let me click on run. So right now we have our global best. Let me click on step, and against the each first iteration, iteration number one, we have the best cost, which is 71.9009. And now next, now we have it, which is 2. Now we are into the second iteration. Now we are into the second iteration, and our population starts again. Okay, let me show you another thing in our particle and in our velocity. Previously our velocity were 0, and right now we have updated our velocity. So as we have updated our velocity, you can see that previously we have best numbers around more than 100, and right now on our first attempt of the iterations, based on the velocities, we have the best number 71. So how this works actually, if we have this kind of space, and we have 10 numbers, let's suppose 5, then these 5 numbers will be just closer to each other, or in the next step they will just move on another side. So that's how they move inside the space and finds the best size, best numbers. Okay, let me explain this a little more in detail. Let me click here and click on step. So now we are in our second iteration, and we have the population of 100, and right now our I is 1, means we have to repeat this loop for 100 times. So right now the particle I want to see, particle best dot cost. Let me select this thing. Okay, so this is the particle cost which actually we get from here. This is the particle cost which we get from here, and this is the personal best, which is not present right here. Means this is the personal best, which is actually we get from this loop. In this From this loop, we have personal best which we stored, and right now in this we don't have personal best. Right now we have this variable particle cost. So if particle I cost is better than, I mean particle I cost is our current cost or current position. So if our current position is better than our personal best position, then we will update this particle I cost with the personal best cost and particle I position with the personal best position. So if our current position is better than personal best, we have updated the personal best, and then we have to compare that with the global best. So if our current personal best is better than global best, we will replace that personal best with the global best. So our global best, let me select this variable. So this is the global best or position. So we previously we have global best here, and here we are just utilizing that global best. We are not updating here. Here at this point we are updating our global best. So that's how it works. And next time, let me click on continue. For the second iteration we have this number. Let me left click here and let me complete the 1000 iterations. So 1000 iterations, you can see that initially we have these numbers 71, and then as iterations proceeding, we are getting the better numbers. And then here we have a plot. Okay, so as you can see that plot, and right now in the start when you click on it, when you click here you can also see the number. So at one position we have 71. So at for 78 iterations we have this number. So from here you can also judge things too. And okay, and now let's get back to the final part. Let me adjust the objective function a little bit. Now let me show you another program where PSO is applied to another objective function or case, which is actually related to load flow program. So here in start of program, let's forget about the cases. uh, let's talk about this thing. So here number of DGs, distributed generations, which is defined here, which you maybe between 4 5 6. Okay, let's go with the 4. Let me click here, and number of DGs 4. Let me consider with the case 1. So case 1 means we are into this, and a number of digits 4 means we have to repeat this loop for 4 times. Let me click on step. So here I have to define the variable var min and var max. So it's a variable, and it's actually a variable with var min and var max. So var min will represent the lower bound, and this is the upper bound. So for example, if the dg size as we have 4 digits, 0 0 0 0 4 sizes, and they will be the 4 locations. So the first minimum locations will be 2 2 2, and as per 69 and 3000. So in max we have 3000. Again we have 3000. Let me write it x. Again we have 3000. Let me write x. Again we have 3000, and right now we have 69. So let me rewrite it as y. So right now we need to have a var minimum and var maximum. We need this kind of a matrix, or this kind of a matrix. So here we have 1 multiplied by 8. So here we have nvar as 1 multiplied by 8. 4 will be the sizes and 4 will be the locations. var min we have 1 cross 8, and var max we have 1 cross 8. So here we have 4. So let me click on step. We have 0 and number of dg, I means 1 plus 4. So at fifth location, so this is we put 0 at the first location, and n plus number of dg. N is 4 and n is 1. So at 1 2 3 4 and 5. So at fifth location we have 2, and then in max at 1 we have 3000, and at 5 we have 69. So from here you can, at 1 we have 3000, and at fifth location we have 69. So when we run this program 4 times, so when we run this section 4 times, as the number of digits are 4, 4 times this loop will runs, then we have this kind of in and this kind of it out. So based on our requirement, we can generate any kind of input and output. And here in this section, which is actually the case 3, so here we have to generate real and reactive. So as I explained previously, you may just consider this thing, and in this case we have nvar which is 12. So right now we are nvar 8, and in case 3 we have 12. Why 12? Because these 4 will represent the real powers, and here at this point we have to reallocate, or we have to assign another 4 as q, and then next 4 will represent their locations. So that's achieved from this section. Okay, let me click here and let me click on continue. Let me show you var min. You can see that as we have case 1 we have 8 numbers, and in max we have 8 numbers, as I explained previously. And right now at this program, in previous program our objective function was the cost function. Okay, you may give it any name. Right now we have our load flow. So in our load flow, let me left click here and click on continue. In load flow program, what I have to put as an input, so particle I position, let me copy this thing. So from where I get the particle position, previously this thing. Right now at this point, based on the min, max, and the number of the variables, a number of the decision variables, I have created the position variables. Okay, let me copy this thing, let me put here. So this I have to multiply this thing with the 1000. So these 4 are the locations. When I multiply 1000 with it, it will be the 55 This one will be the 11.5, which will be estimated to 12. This will be the 30 location, and this will be the 63rd location for the DG. And these will be the sizes, as I have to multiply these things with the 1000. And later on in the load flow program, let me click on continue. Okay, right now as a DG I have 4 DGs, and as this, so this is the same variable, same numbers which I get from here. So that's how I can put the numbers into my load flow program. And this is same PSO code, sorry, this one, this is exactly the same PSO code, get from the yarpis and just do a little modification in it. And that's how it works. So based on that, you can easily modify your objective function and achieve your requirement. So if you found this video really helpful, give it a thumbs up. And if you are looking for a different kind of optimization explanation, you may put it into the comment section. And a comment which gets more likes, I will definitely make another video on that optimization algorithm. So share it with your friends. Definitely it needs dedication and hard work to create such kind of videos. So subscribe the channel. Thanks for watching.